Before I start, I'm just remind you we have a question about Euler method and how to use Euler method to solve second order differential equation, or you can solve system of first order differential equation. Okay, how to solve this one in general? Okay, so the solution of this one, I can reduce by reducing the order, by reducing the order. Okay, how you can reduce the order? You just let whatever you have, you can call y dash or ui I dx equal to u, right? So this is your first differential equation. If you substitute in this equation, y double prime plus 2y prime plus 3y equal to 0. You substitute by u equal to y prime. So you will have what? You will have u prime plus 2u plus 3y, right? Equal to 0. I would like to have this system of differential equation, so I will have u dash equal to minus 2u plus minus 3y, right? So yes, this is my second differential equation. I think we know how to solve system of linear differential equation, right? Using the eigenvalues and eigenvectors. If you remember this one, right? How to write this system of differential equation? How you can write these two? You can write it as, what is your variable here? You will have y dash and you have u dash equal to, you have a matrix. What is the coefficient matrix here, please? Multiply by the variable. What's your variable? Y and u. Okay. If you have constants, okay. Can you give me the coefficient of the matrices, please? Can you give me the coefficient matrix? Hello, guys. Can you give me the coefficient matrix? Do you think this is the right coefficient matrix? Find the eigenvalue and eigenvector by MATLAB, please. So I remind you, you have y dash, u dash equal to minus 2 minus 3, minus 2 minus 3, 0, 1, and you have y, u. Okay. So your A, what's your A? Yes. Yes, by MATLAB, please. Yes, by the MATLAB. Muhammad Raid, Check your computer, Muhammad. Thanks for Shemash. She gave us the eigenvalues and eigenvectors, -2 and 1. And thanks for Musab. He gave us V1 eigenvectors. V1 equal to 1 and 0. Okay. And V2 equal to -0.707 and O positive 0.707. Thank you, Musab. Thank you for Shema. Now, how to write the solution of this one? The solution or the exact solution, not the numerical one, is y u equal to what? C1, and you have to write the V1, 1 and 0, and you have to write e to the lambda 1 minus 2t plus C2, and I have to write V2 minus 0.707, positive 707, and I have to type multiply by e to the t. This is the right formula for your solution for u, for y and u, right? You see what I mean? But my independent variable here is x, not t, right? So I'm not going to write t. I have my independent variable is not t, it is x. So I have to change this one into x, okay? So this is how to solve this one using the eigenvalues and eigenvectors. And this is the formula. If you miss to type the vectors, so your solution is wrong. Catch my point? So we got the exact solution. So I'm going to write only y, okay? Y equal to what? C1 times the first component of this one, e to the minus 2x, plus C2. The first component of this one is minus 0.707 minus minus 0.707 times e to the x times e to the x. So this is my solution, right? Now I have the initial value. What is the initial value here? The initial value y at 0 equal to 1, as y at 1 equal to 1. So I have to use this one to find the C1 and C2. Y at 1 equal to 1. So 1 equal to C1 e to the minus 2 and x is 1 plus C2 minus 0.707 e to the 1, right? This is my first equation. Now I'm looking for the second one. The second one depends on the second initial condition, y dash of 1 equal to 0. I have y dash of 1 equal to 0. Y dash is what? Y dash is u, right? So u at 1 equal to 0. Yes, what's my u? My u is the second component here, right? Okay, so u equal to C1, u equal to C1, and the second component is 0. So here 0, no need to write anything else because the power of this one would be 0, plus C2, the second component, plus C2, positive 0.707 times e to the 1 because x is 1, e to the 1, okay? So u at 1 equal to 1. So this is u at 1 equal to 1. Okay, to 0, sorry. So now I know from this one, this is 0. So C2 times 0.707 E equal to 0. Never this one be 0. So C2 equal to what? 0. Once I have C2 equal to 0, I substitute in number 1, right? C2 equal to 0, this one will be 0. So C1 will equal to what? So C1 equal to 1 over E squared, right? Now I can type my solution will be y equal to C1 is 1 over E squared okay. Now just substituting by C1. What is C1? 1 over E squared. This is 1. E to the minus 2x. C2 is 0. I finish. So this is my solution. This is my solution. Easy? Yes. This is when you have the theoretical solution. Now we will try to have the numerical solution. Now I will let you watch this video to see how to find a solution of the system of linear differential equation. We use the eigenvalues and eigenvectors to find the solution for. Okay, please listen to this guy for a minute.
Is write this in matrix form. I'm going to need that later, so I'm going to do it, although I don't need to for this part of the question. So it's that, and I can write that as 0, 1, negative 3, negative 2, times y1, y2. And that's it. Okay, part B says, find an approximation to y of 1.2 using h is 0.1. So I'm going to need to do 2 steps. Oh, by the way, in this one, I was given that y at 1 is 1, and y dashed at 1 is 0. So I really should have put y1 equals 1, y2 equals 0 at 0.1. So I'll put that in there. I'm going to use the forward Euler with h is 0.1, and we just need to remember that yj plus 1, the next approximation of y is the previous approximation of y plus h times a times yj again. This is a here. Now I know a first approximation, a first guess is 1, 0. So y1 will be y0 plus h is 0.1. A is my so it's going to be 1, 0.1 minus 0.3, 0.8. So that's going to be what I'm going to multiply by each time. So if I multiply that by 1, 0, I'll get my first iteration. That's 1 times 1, which is 1. And that's minus 0.3. So when x is 1.1, y is 1, and y dashed is approximately 0.3. So if I want the next iteration, it's going to be y2, the next one. It's going to be that same matrix, 1.1 minus 0.3, 0.8. Times by the estimate I got for 1.1, and then I'm going to multiply that out. That'll be 0.97, and that'll be minus 0.54. So when x is 1.2, y is approximately 0.9703 big. Now for B part 2, it said use the backwards Euler. So for the backwards Euler, we've got yj plus 1 equals yj plus ha yj plus 1. So this is the one where we've got to rearrange.
What's your Euler formula? Your Euler formula is yi plus 1 equal to yi plus your h, your step, times the function the function here of if it is x, okay, and if it is whatever y here is okay, right? So this is the Euler for only one equation. For a square matrix, you will have here a vector of y1, or you can call it whatever you like. You can call it u and v if you like to call it u and v. So here you have u naught and v naught, right? Plus your step here h, and this is what, instead of f, you have the coefficient matrix here. Okay? So you have the coefficient matrix here. This is a coefficient matrix. A11, A12, A21. Right? So this is the point of having the Euler method using the eigenvalues and eigenvectors. Okay? This is how to write the Euler formula. Okay? For this system, you are going to solve this system here. You have a system, you du y dt, or by dx, it's up to you, y dt equal to a function of u and yes, v and t, and you have the other independent variable dv y dt as another function, I call it g of u and v and t, right? So this is can be transferred into the system u v dash equal to a coefficient matrix A, okay, or I can call it a matrix, okay, and you have your variable here, right? So this is a coefficient matrix here, must be squared. So to solve this system of differential equation, you can use Euler, but instead of having this formula, you can have the vector formula like this one. Okay? So Yes, again, this is to have U1 and V1. If you go for U2 and V2, so U2 and V2 will equal to, again, U1 and V1 as a vector, U1 and V1 as a vector, plus this step H and multiply by the coefficient matrix again. Okay, and you have U1, V1. Okay, and this is a constant. Also, to go for U3, you will have the previous one, and you end up with finding the solution of U, and you have here X, and you can have X here and V, so you can graph both these two independent variables. Okay. And instead of just using Euler formula for one first order differential equation, okay, you can use Euler as a vectors, right? So U1 and V1 equal to Y naught V naught plus H and the coefficient matrix U naught V naught, and to solve this system of two differential equations. And U2 V2 will be U1 V1 plus your step and the coefficient matrix U1 V1, right? Be careful when you have this one as a common factor. Similar here, when you take this one as a common factor, you take it outside U naught V naught here, and here you will have this A1, A12, A21, A22, right? And you have H. So here you have the identity matrix 2 by 2. What is the identity matrix 2 by 2? Is 1, 0, 0, 1, right? So this is how to solve this one, right? I'm just having a question for you. You know how to reduce the order of the differential equation, so you can change the second order differential equation into two first order differential equations. Now I'm asking you to solve this one. Can you solve this one, please? This question I'm writing for you. Can you use the eigenvalues and the eigenvectors to solve this system? Most of you says yes. And when I'm asking, okay, what is your coefficient matrix? You agree with me that your coefficient matrix is t minus 3 and t and minus t squared. Sorry, I forget the square here. Okay. So can you find the eigenvalues and eigenvectors this one? Of course not, because this is not a constant, right? Okay. So yes. So we have to solve it by what? We have to solve it using what? Euler method, right? Thank you very much. This is my point for this tutorial. Just to convince you, sometimes when you start to solve, theoretically, you have to go to the numerical solution. Catch my point? Okay. I will leave it for you and see you, inshallah, on Tuesday morning. You give me the solution for these two system of linear differential equation, first order differential equation. Okay, I'm waiting you on Tuesday, inshallah.